I now call to order the lecture portion of the Society's 2,520th meeting in what is now the 154th year since its founding on March 13th, 1871. Good evening, everyone. My name is Larry Milstein. I'm the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry to as broad an audience as possible. Welcome to our members, guests, and friends to the lecture part of today's PSW meeting and to the lecture by Will Marshall on Planet's small satellite constellation that images the Earth's entire landmass at high resolution and high frequency. Before we go further along, let's take a moment to thank the sponsors of PSW. Keep in mind, we don't charge for admission here. So all of this is supported by generous donations. And the Society is grateful to our full year sponsors, PSW member Mike Helton and Helton Associates LLC. Thank you, Mike. And to the 2025-2026 full year sponsor, PSW member Joe Schulman and the Schulman Foundation. Thank you, Joe. And we also are very grateful to the sponsor of tonight's lecture, one of several that he sponsors, and who is a very, very active member of PSW and a good friend, PSW member AC Charania. AC! Oh, he's a little shy, I don't want to say. The Society needs your support to meet its expenses. So if you've not given or feel you can give a little more than you have, please do not hesitate to donate. If any of you are interested in sponsoring a lecture or becoming a full year sponsor, please come talk to me. I will be available afterwards at the social hour and beyond that. And you can, of course, email me. You can call me. I'd be happy to speak with you. So please don't be shy. All right. I am pleased to announce the following new members. We had 25 applications for new membership over the summer. I think we're past COVID now. The previous number for the summer, record, 6.
Wow.
So this is very good, bodes well for the year. We usually read out names, affiliations, interests, and how they learned about the society, but I think it would be too time-consuming to do that. So I'm just going to name them. I just want to note that, in general, more than half of the new members found PSW through YouTube and social media. And several new members noted specifically, as I mentioned before, that they were attracted by the depth of the programs. So I think we're doing something right. Thomas Kostach, Michael Idiamarco, Ben Anderson, Samuel Connors, Ina Anderson, Ginger Greenfield, Melena White, Justin Friend, Monique Gingold, Karen St. John, Neil Rockland, Mary Moore, Eric Teo, David Briss, Michael Mazer, Gordon Moore, Michael Martin, Ray Alimento, John Saveland, Aoki Williams, Jessica Baker, John Muda, Richard Noteboom, and Prithviraj Mukherjee, Humberto Caldelas, and tonight's speaker, Will Marshall, who learned a PSW from our invitation to him to speak here tonight, and whose interests certainly will be clear from the lecture. Please join me in welcoming them all to membership. All members are entitled to a signed copy of Compendium Volume 17, first edition of the Bulletin of the PSW. And if you haven't received yours, please come see me after the meeting and I will be glad to give it to you. All members are invited to the pre-lecture receptions and dinners with the speakers before each lecture. Yeah, pre-lecture before each lecture. Yeah. For camaraderie and interesting discussion, if you're interested in membership, you can access a membership application on the PSW website by clicking the blue join button at the upper right-hand corner of the home page. If you're here in the Powell Auditorium, business cards in the back, they have a QR code to take you right to the membership application form. Everyone with a genuine interest in science is welcome to apply for membership and join. All you have to do is pay the $75, now worth only $25, counting for inflation, membership dues. And with that, Scott Matthews will now present the minutes of two meetings, one long, one short. The first is the 2,518th meeting and the 94th Joseph Henry Lecture by Jason Dworkin on the analysis of samples brought back to Earth from the asteroid Bennu by NASA's OSIRIS-REx mission. And he will also more briefly report on the annual members business meeting at the 2,519th meeting of the Society on July 18th. Scott.
Thank you, Larry. Good evening. On June 27th, 2025, members of the Society and their guests joined the speaker for a reception and dinner at 5:45 p.m. in the members' dining room at the Cosmos Club. Thereafter, they joined other attendees in the Powell Auditorium for the lecture proceedings. In the Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the lecture portion of the 2,518th meeting of the Society to order at 8:05 p.m. Eastern Time. He began by welcoming attendees, thanking sponsors for their support, announcing new members, and inviting guests to join the Society. Scott Matthews then read the minutes of the previous meeting, which included the lecture by Alex Creeley titled Commercial Fusion Power, High-Temperature Superconducting Magnets, and Compact Tokamak Power Plants. The minutes were approved as read. President Milstein then introduced the speaker for the evening, Jason Dworkin of the NASA Goddard Space Flight Center. His lecture was titled OSIRIS-REx Brings Samples of Bennu Back to Earth. The speaker began by saying that, quote, rocks remember, and that Bennu represents the type of materials that bombarded the Earth billions of years ago. He said that rocks from Bennu additionally contained information about the processes occurring in the early solar system. Dworkin discussed remote spectroscopy, indicating that while remote measurements can provide several types of information, detailed analysis, particularly with respect to organic molecules, requires physical contact with the sample. The speaker discussed the fact that meteorites provide significant information, but there are always questions about the provenance, the source, and the possible contamination of samples. Pristine samples must be acquired directly from the source, hence the need for sample return missions. The speaker then discussed the history of sample return missions, including the Apollo moon missions, the NASA Genesis and Stardust missions, JAXA's Hayabusa and Hayabusa 2 missions, the Tianwan-2 mission. He discussed the goals of the OSIRIS-REx mission, including returning samples of pristine carbonaceous asteroid, providing ground truth for remote observations, asteroid resource identification, security by better understanding the Yarkovsky effect, and the regolith mapping on a sub-centimeter scale. Dworkin discussed the process by which Bennu was chosen over other candidate asteroids. Bennu turned out to be the only carbon-rich asteroid with a diameter greater than 200 meters with an optimal orbit for sample return that had been well studied by ground-based telescopes. The speaker then discussed some of the details of the OSIRIS-REx spacecraft, showing images and animations of the instrument deck, the actuated solar panels, the sample return capsule, and the sample collection mechanism, or TAG-SAM. Dworkin discussed the path to launch, including the original proposal, the precursor missions, the construction of the spacecraft, and the launch in September of 2016. He mentioned several problems that occurred along the way, including a fire that destroyed critical components, an explosion and fire on a nearby launch pad, the loss of cooling water which jeopardized the spacecraft's batteries, a forest fire close to the Canberra communication station during approach, and a nationwide internet outage and brief failure of the deep space network during critical maneuvers. Dworkin then discussed some of the details of the OSIRIS Rex mission, including launch, outbound cruise, approach, preliminary survey, orbital A, detailed survey, orbitals B and C, rehearsal, sample collection, post-tag observations, return cruise, and return. He described the imaging of the tag site, the sample collection site, and the fact that the spacecraft was able to tag 73 centimeters from the center of the desired location. He showed 3D images of the collection site before and after tag, indicating that the tag crater was approximately 9 meters across and 68 centimeters deep. He showed actual video of the tag SAM collecting the samples from the surface of Bennu and penetrating about a half a meter into the asteroid during sample capture. He showed videos of the sample return capture, re-entering the Earth's atmosphere, and landing safely under parachute in the Utah desert. Dworkin discussed the process related to handling the sample return capsule. These included documenting, bagging, securing, transporting, purging, and finally opening the capsule. The mission yielded more than 120 grams of pristine regolith, about double the requirement. The speaker described how Bennu samples are being distributed amongst several international labs, 14% currently being studied at NASA Goddard, 0.55% being studied at JAXA, 4% to the Canadian Space Agency, and the remainder being stored by NASA's Johnson Space Center for future study. Dworkin then listed several of the scientific techniques used to study the Bennu samples, including FTIR microscopy, gas chromatography, mass spectrometry, isotopic ratio mass spectrometry, SEM and TEM microanalysis, X-ray absorption spectrometry, etc. He described some of the results of this analysis. These included that most of the samples were dated between 1 million and 6 million years old. Some of the silicon carbide grains predate the formation of the solar system. The precursor asteroid from which Bennu formed contained large amounts of water. Bennu contains high amounts of ammonia, and all the DNA and RNA nucleobases have been detected. The speaker ended his talk by saying that even with several disasters and a global pandemic, the launch was on time and under budget, and it, quote, has been a remarkable team, end quote. The lecture was followed by a question and answer session. A member asked about changes to the sample after collection and return. Dworkin indicated that the pristine, inert storage environment should prevent any significant changes, but that researchers are aware of fractured rocks where the two pieces fit perfectly together, and it is difficult to determine whether these fractures occurred before collection, during collection, or during the return mission. A member on the live stream asked why OSIRIS-REx emphasized the collection of regolith over subsurface samples. Dworkin responded, quote, cost. He explained that drilling down into Bennu would significantly increase both the risk and the cost of the mission. A guest asked if there were any conditions under which inorganic compounds could have been transformed into organic compounds. Dworkin responded that to some extent, it depends on how you define organic and inorganic. But he said that it was not easy and, quote, he would not bet on it. After the question and answer period, President Milstein thanked the speaker and presented him with a PSW rosette, a signed copy of the announcement of his talk, and a signed copy of Volume 17 of the PSW Bulletin. He then announced speakers of upcoming lectures and made a number of housekeeping announcements. He adjourned the 2518th meeting of the Society at 10:04 p.m. Eastern Time. Temperature in Washington, D.C., 25.5 Celsius. Weather, mostly cloudy. Audience in the Powell Auditorium, 97. Viewers on the live stream, 47, for a total of 144 viewers. Views of the video in the first 2 weeks, 376. Respectfully submitted, Scott Matthews, Recording Secretary.
Scott is a physicist, and it's very, very thorough in his minutes. Do we have any additions, corrections, comments on the minutes? Hearing none. Oh, we got one. Robert, the comment is, was the age of the samples from Bennu are not million, it's billion. Yeah. Also, you said that was a Requirements for membership are an interest in the society, but the requirement is a genuine interest in science. You don't have to care about the society. With that, those corrections, we will, yes, yes, no? Okay, if there are any other comments, corrections, if not, well, thanks Scott again, and those minutes will be posted to the website in due course. Now, I should add a comment because I've had questions about why we bother with the minutes. Aside from it being a lovely tradition and putting our volunteers to work, you can find out what happened in a lecture in about 3.5 to 4 minutes by reading the minutes. To watch the videos, that take you an hour. And so the minutes are very helpful. Plus, they're written, and we like to exercise our ability to read. Yes. The comment was that the minutes are very valuable. They really help understand the videos. Thank you. All right, so we're going to move on now to the main attraction of tonight, and we'll turn to tonight's lecture by Will Marshall. Will is co-founder and chief executive officer of Planet Labs PBC, commonly known as Planet. I shouldn't say commonly, I should say known as Planet, the leading Earth imaging and geospatial data company. Previously, he was scientist at NASA Ames Research Center working on small spacecraft development. At Ames, he helped formulate the Small Spacecraft Office, was a member of the team for the LADEE and LCROSS lunar missions, served as co-PI on PhoneSat, and worked on several space debris remediation projects. Will's work focuses on satellite constellations for near real-time imaging of Earth and on methods for reducing the cost and complexity of space missions through miniaturizing satellite technology and other things. He's an author on numerous scientific publications and has contributed widely to public discourse and policy formation on the role of space technology in sustainable development and global transparency. Among other honors and awards, Will was named a Young Global Leader by the World Economic Forum and one of the most creative people in business by Fast Company. He is a co-recipient of the Royal Photographic Society Award for Environmental Responsibility, and he and Planet have been recognized as tech pioneers by the World Economic Forum and by numerous space and technology industry groups. He earned an MS in Physics and Space Science and Technology at the University of Leicester, I think. Leicester, sorry, University of Leicester, and a PhD in Physics at the University of Oxford. All questions will be held until after the lecture during an extended Q&A period. And with that, Will, the stage is yours.
Good evening, everyone. So I'm looking forward to this discussion. I'm going to leave plenty of time for Q&A. Can everyone hear me okay? Super. Okay, let's get in. So space and AI. We wanted to talk about this, and Larry asked me to start with a few remarks about my background. And so I chose to focus on a couple of my inspirational mentors. And starts with this guy, Patrick Moore, who this is me when I was 17. I built this telescope on the left, and Patrick Moore was an eccentric astronomer. There's just at the very least, you can see with his monocle up here. So yeah, Patrick ran this program called the Sky at Night in Britain. It was a popular space program. It's a bit like Carl Sagan of England, but much more eccentric. Anyway, he guided me a little bit, and then here's me doing my PhD. Got a little bit more serious, but here my professors Dirk Baumeister and Roger Penrose, where did quantum optics and looking at studies to look at foundational issues between quantum mechanics and general relativity. And then my third mentor to speak about is Pete Worden, and he was the director of NASA Ames Research Center and a sort of maverick guy who oversaw that NASA center, having been an Air Force general, but also a PhD in astrophysics. And he really shielded us for enabling us to do a little bit more out-of-the-box thinking, as you'll hear about. And it starts with this one on this slide. So the L-Cross mission was one of my first exciting missions that I was part of at NASA. And this was a mission to the moon, looking for water on the moon. And excitingly, we found lots of water on the moon, about 5 or 6% by mass in the area we impacted. So it was an impactor that slammed the south pole of the moon in one of the permanently shadowed craters, and the plume of material was then subsequently flown through. So we actually directed the upper stage of the rocket into the moon, and then this probe that you see, the spacecraft here, flew through the plume before its own demise, but gave us a couple of gigabytes of data, which took a couple of years of my life, but did for us scientists, we like the front covers of Science magazine. And I was just sitting next to Marshall McNutt, who was the head of AAS at that time. Anyway, so one of the interesting features of this mission was that we did it in only a couple of years, and it cost $79 million, which sounds like a heck of a lot of money to most people. But for NASA, this was bizarrely cheap, because everyone at NASA headquarters told us that we couldn't do such missions for under $1 billion. And we'll get into why a little bit. But it got us thinking about, could we do spacecraft missions radically lower cost than that? So a colleague of mine at NASA had kept on holding up his phone when he was in our office and saying, "This has most of what a spacecraft has. Why are we making them so much more expensive?" In particular, they have fast processors, they have radios, they have, of course, camera systems, they have accelerometers, they have... If you look at the list of things a spacecraft has, and you look at the list of things a smartphone has, it's probably 90% overlap. And so we took him seriously one day and threw a few into space, and to see if these things would work in space. And they work just fine. And these pictures you see here aren't very impressive pictures of the Earth. Obviously, more impressive pictures of the Earth have been taken, but they were taken from a phone camera that cost a few $100s. And we were asking the question with this technology experiment: if this costs $500 and a normal spacecraft mission costs $500 million, what are the extra 6 zeros doing for us? And that is what led to this, which was we started Planet as a sort of spin-out out of NASA to experiment with much lower cost ways of doing spacecraft, and leveraging some of the innovation that had been done by many others on faster, cheaper, better spacecraft missions, like Surrey satellite technology and some of the US Air Force work in this. And classically, we were always told that you can't do you can only do 2 of those 3 things, faster, better, and cheaper in space. Pick your 2. But we were really trying to do all 3. And so we left NASA to try to do that, and in particular, with a goal stated here, which is to image the whole Earth every day and to make change visible, accessible, and actionable. And the concept was very simple. We live on this beautiful spaceship called the Earth, all 8 billion of us astronauts, and all the life on it, trillions of creatures. And how can we take care of it if we don't have data on the timescale of the change that we're making? So you can't manage what you don't measure. If we have these challenges around the planet, and here's just 3 of them, there's obviously myriad more, you need data on a timescale of change that is happening to intervene. And actually, sometimes to my space friends, I make the analogy that on a spacecraft, of course, if a spacecraft is spinning at, say, 1 hertz, you better not be measuring it once every hour if you want to stop that spin, right? And humans were operating this spaceship Earth with measurements of the Earth once every month or so from Landsat, but our operational cadence as humans and our interventions take place on days or hours sometimes, or weeks. But if we want to do something about that, and that is to take care of our spaceship, we better do something faster. So we set about this, which was essentially erecting a line scanner for the planet. The idea was to put up more than 100 spacecraft we calculated we would need to take each one taking a strip map of the Earth's land as it went over in a polar orbit, a sun-synchronous polar orbit, and then, but collectively, they would end up line scanning the planet. The Earth does the legwork in doing its nice rotation. The satellites actually stay fixed with respect to the sun in their angle. Sorry for the extra lines, but we then launched a bunch of others in all sorts of other orbits. But basically, we line scan the whole Earth every day at 3-meter resolution, 8 spectral bands. And then we have a set of 15 satellites that can zoom in on any particular location up to 10 times per day at 50-centimeter locations. So think of it like a scan system for peripheral vision, and then a zoom-in system. So we went about doing that, and how and why we're in a position to be able to do that is based on a few different revolutions that are happening in the space sector. It really is a burgeoning time right now that we've got to leverage. The first piece of it most people have heard of, which is to do with rocket costs coming down. Rocket costs have come down about 4-fold over the time period that we've operated the company. Primarily, this is SpaceX reusable rockets bringing the launch costs down. And it's been a tremendous service to the space sector, obviously enabling more. But a lesser known aspect of what's really undergoing the space revolution is the capability performance of satellites. So we've taken satellites that are about the size of this room, literally, double-decker bus, and shrunk them in size, basically looking at the miniaturization of electronics and therefore enabling spacecraft to be much smaller for the same capability or equivalent capability. The upshot of both of these, of course, are synergistic. Cheaper launch and increased capabilities, but the 1,000 times increase in capability per kilogram you put on the spacecraft, on the fairing of the rocket, is, I think, the dominant factor that's changing the game in space. And the upshot of both of these things is all nothing to do with space. It's nothing to do with rockets or satellites or space of any kind. It's actually to do with data, and it's all to do with the Earth. What we have effectively got is about 10 times or more Earth imaging data than we had just a few years ago. And we've got more than 10 times more bits flowing around the Earth for telecommunication satellites, primarily through Starlink. So basically, all of it's about data. Space and data are married. This is just to give an illustration of the size of our spacecraft compared with Landsat. They're very diddy. Landsat is, of course, an incredible mission that has done the legwork in helping us to be aware of the basic changes that have been going on the planet for the last 40 years now. And we really try to build off that legacy in just adding greater spatial resolution and greater temporal resolution. But just to be clear, these missions are still necessary because we calibrate our satellite data to these satellites. Actually more to Sentinel-2, but also MODIS and Landsat. And so this is our complete fleet today. I'll spend a few moments on each satellite type. So the Dove satellites, we have about 150 of these in orbit today. It's the largest Earth imaging constellation. Each one has 3-meter resolution and has these 8 spectral bands. They more or less mirror the Landsat bands and the Sentinel-2 bands, which are more or less the same in the optical and near-infrared spectrum. You can see the spectra here. And we image 200 million square kilometers a day. So the Earth's land mass is about 150 million square kilometers. We do all the land, and we do some various parts of the ocean, like the Mediterranean, the Caribbean, the South China Sea, anywhere there's hotspots, basically. And just to give you a sense of the scale, we take 4 million 47 megapixel images per day. So it's a gargantuan amount of data. It adds up to about 45 terabytes in its most compressed form, although it's a fair bit bigger than that once we decompress it and do the analysis on it. And so we are generating gobs of data about the planet. And there's we'll talk about AI coming up and the utility to extract out information from it. So we have all these different layers for every. So we have now, on average on the Earth, 3,000 images for each point on the Earth's landmass, and each one has these 8 spectral bands. useful for various different functions. Then there's the Pelican spacecraft. This is our next generation high resolution satellite. We just launched 2 more last week on a SpaceX rocket. These ones are, we call them 30 by 30 by 30 by 30. So they are 30 centimeter resolution, 30 revisits a day, and 30 minutes from our task request to get the image back. So super important for disaster response, various security applications. So we now have just got up to 3 of these blighters in orbit, and we just got our first light off these the other day, so it's really cool. And then Tanager is our first hyperspectral instrument in orbit, and we're really excited by this one because as a lot of people know, if you really want to understand things, taking spectra is one of the best ways of doing so. This is a 400 spectral band instrument. It was developed by NASA JPL, and I think the first one cost about $50 million for the instrument, and now we have taken that instrument and figured out how to produce them more efficiently and build these spacecraft such that the entire cost of the spacecraft, including the instrument, the spacecraft and launch, is about $6 or $7 million. So massive reduction, and the great thing then is that we can launch these at larger scale for important missions around the planet. And this one, its first mission is, I want to spend a second on this collaboration because I think it's really cool. It's a public-private partnership where NASA JPL, as I said, provided the instrument technology, and we provided the spacecraft bus. Carbon Mapper is a non-profit organization that developed this portal for looking at methane data, but they also provided the funding for this. It's a philanthropically funded mission, and it's a fun way in which public-private partnerships can happen that can enable us to speed up getting exquisite instruments in space. Those folks at JPL really wanted to fly a bunch of these missions. There wasn't the budget for that, 300 million or 500 million spacecraft costs. Here we came along, we can do it a little bit cheaper, or about 50 times lower cost. And Carbon Mapper provided a philanthropic funding because they recognized the need of getting these up there to do this carbon mission. It was a really cool collaboration. I was a little bit worried about impedance mismatch between us and JPL because we tend to operate very speedily. And I worked at JPL early in my career, and it's less speedily, but it worked really well. And we got these instruments in space, and its first mission is methane detection. And that only really uses a couple of the 400 spectral bands. There's lots of exciting other things that it can be used for. And here's the first light from last year, and this is just showing a few of the spectral bands. So this was its mission, which is to look at methane gas emissions and to find them. So methane gas is one of the biggest climate forcing functions for global warming. And here's an example where we have started to release locations around the world where we see gas emissions. We've released about 3,000 or so locations. This is an example where as soon as we put the location online, someone went and realized that they had a big gas leak. This is the first one that happened like this. This gas leak is about 7,000 kilograms an hour of methane, which is roughly about the same as, I think, 10,000 cars driving at full speed on the motorway, or about 100,000 cars or 200,000 cars if you take into account the duty cycle of car use. So we estimate that if you could take care of about if you could do this about 100 times per month, you could take out about the equivalent of the US forcing function of all the cars in the United States. And so it's really exciting, the potential. So we've been, it's been even more sensitive than we thought. We got down to 66 kilograms of methane per hour. That's roughly the same as having 4 houses turn on all their gas oven and letting that go out, so we can detect small amounts of methane by global standards. And the primary sources of these are gas facilities like gas pipelines and oil and gas stuff, but also all the cows and then the waste facilities. So we're looking at all of those and trying to help people stop that methane. It's one of the lowest hanging fruits for stopping global warming. We also did a partnership with California to monitor these on a systematic basis over California, and they're paying for this data over California. So the general aim of all of these satellites, one is sustainability. Obviously, the sustainability applications per that methane example are kind of clear, but I could talk about a couple. And then digital transformation is industries around the world trying to become more efficient and effective. And then peace and security is our other big one. And we spend a lot of time, I mean, basically doing a global transparency maneuver, which is having big implications for understanding events relevant to security. And I'll get into a couple of examples. Can you play the video on this one? This was sticky if you can play the video. This is I'm going to just show a couple of use cases here. Here, if you press that button now, let me see if I can. Oh, did I do it? There we go. So in agriculture, it's not only that we can see every farmer's field every day and track, but one of our spectral bands, the near infrared, can be ratioed with the others to enable us to detect the type of crop and the crop yield on every 3 by 3 meter pixel across the entire Earth landmass every day, about 30% of which is agriculture, and plot agricultural yield over time, and then help farmers to improve crop yield. That's both good for agriculture, improving crop yield efficiency by about 20–30%. On the other hand, that also stops pressure on deforestation, which is primarily driven by agricultural expansion. We work with utility companies like PG&E in California to try to prevent fires. So in this case, monitoring hundreds of thousands of kilometers of just their power lines every day and telling them where the brush is getting too close to the power line to do preventative work. About half the fires are caused by this kind of problem. We do some fun things like stopping marijuana. Actually, in a lot of countries, we just had another case in Panama and the Darien Gap that is leveraging our data to stop it. In this case, it's legal in Humboldt County, but you still need a license. And it seems like a lot of them don't have a license, but it's actually an interesting way of doing, if you like, automated enforcement of permits across states. So various states use our data for that kind of purpose. This was another interesting use case in insurance where instead of having to send people out to check on claims, they just do automatic checks on this. Swiss Re and AXA, the two big insurance companies, and they look at our soil moisture data. We have the amount of soil moisture in the top 5 or 10 centimeters of the soil, and this helps them to, and basically if it's less than X amount of water for more than Y days, they send out the adjustment instead of having to send out a person. And then, of course, my favorite use case of our data, which is on deforestation and trying to prevent it, of course. And this is just a time lapse of some of our data looking at deforestation, in this case in Brazil. But this is a more hopeful story, which this is a case where we use automatically an AI system to look across the whole of the Brazilian Amazon for new roads, because new roads are normally the sign of illegal deforestation. So we have an AI system, looks for all new road starts across the entire Brazilian Amazon once every week. And it provides then alerts to the Brazilian Federal Police, who then intervene in that situation. One of the best use cases I've ever heard. And last year alone, they did 3,000 interventions, so about 10 per day, seized $2 billion worth of assets, and most importantly, reduced their deforestation rate year on year by 55%. So if you like, real-time information with AI analysis together with cooperative governments can go a long way really fast with this kind of tech. And Polícia Federal, just to give you a sense, have 120,000 people looking at our data every day. So it's quite an extensive system down there. But that's not where we're stopping. On forests, we've now launched this thing called the forest carbon planetary variable. So this is our attempt to estimate not just whether the tree is there or not, but the amount of carbon in that tree. So we've combined LiDAR data in local areas where we have it, together with ground data of people using tape measures to measure tree trunks and species types to then calibrate an AI model that can estimate the amount of carbon in a tree. And it can do so pretty accurately. And so now we have this that you can basically pick your area of the Earth, and it will tell you how much carbon is in all the trees in that area. And of course, this is critical if we want to do carbon markets, if we want to integrate carbon or climate in general into our economic system, integrate that externality in. Right now, we're not doing that, a lot to do with the fact that there's not a consistent measurement system to underpin that. So we're taking away that excuse, or that's the idea. Let me move on to security. We do a lot of work in security as well, and I think it's a really important mission of Planet that we bring this transparency to global events and helping countries to understand what's going on and bring accountability to those situations. So here's Ukraine, and we image all of Ukraine every day as we image everywhere else. And I'll share a couple of examples of how we were helping Ukraine from day one. And in fact, this is day -1 when the Russian forces erected these bridges across from Belarus into Ukraine. And just the day that President Putin said that they were not invading. And from day -1, we were calling their bluff on everything that happened. This is them attacking power facilities. We work with Microsoft and the UN on to estimate building by building the damage across all of Ukraine using automated damage assessment tools, which, by the way, subsequently we used now on a regular basis, in this case in Lahaina, to do building damage assessment. Now we've got it down. The first time we did it in Ukraine, it took 2 months. This now took two hours, such that quickly after a disaster, in this case the fire in Lahaina, we can get them data so that the medical and other emergency services can get in there really fast and determine which building it's going to. But back to Ukraine, we also, field by field, did an assessment with our friends at NASA Harvest of the crop yields, with the crop types in every field, what fraction was under Russian control, where it was being taken. Some journalists used this to, investigative journalists used this to figure out that the Russians were taking grain and taking it to illegally to Syria and other countries against the embargoes. So that then led to further escalation of economic sanctions and so on. The important thing here was Ukraine is supplying over half the world's grain to the poorest countries around the world. It's the breadbasket, the World Health Organization. Like Lebanon, 80% of their grain for feeding that poor country came from Ukraine. And so a lot of that was being stopped. And then our data was trying to help get that grain out, both for helping the Ukrainian people and others. War crimes analysis is one of the other use cases. So we basically have a digital forensic machine. So when, in this case, a mass grave was found, the question was what led up to that, and can that be evidence of war crimes? And then letting everyone else know when things are happening, because we have various media outlets like the Financial Times and the New York Times. And when Putin said, we don't hit civilian targets, we published the next day on the New York Times, here's the 5 schools and hospitals that were bombed in the last week or what have you. So bringing accountability to warfare, I think, is a whole new thing. Now, it obviously didn't deter Mr. Putin, but my hope is that actually bringing this transparency will make it less, it will deter this kind of action in the future, because everyone will know that everyone will get to see it. On a slightly more fun topic, I want to talk about 5 what we call digital public good projects. This is where, so we're a private company, well, not public, but it's a commercial company, but we have an important mission. It's a public benefit corporation, so we really care about the impact of our data around the world. Obviously, you heard about our NASA heritage. That's our sort of ethos. And this is the first digital public good we did in collaboration with the Allen Institute, which is to map all the coral reef systems around the world and warn of ocean bleaching events or fishing that is against the marine protected area and so on. And actually able to identify the different types of corals under the water. Most corals are in very shallow water. I think 90% are under 15 meters, and at that sort of depth, we can still tell the coral type. And then we revisit that on a regular basis, and you can just go to allencoralatlas.org and look at your favorite coral reef systems and see what you can do to protect them. There's a dive in to my favorite coral reef system, which is in Raja Ampat, and there it overlays the marine protected areas where there's bleaching events for regular intervention. And the second one I want to tell you about is one on tracking deforestation. So in partnership with Norway, for several years, we provided data to help track deforestation across 64 countries with their forestry ministries, getting our daily alerts of where deforestation is, a bit like I was talking about in Brazil. This is a slightly newer one. We launched it 2 years ago. This one is mapping all the global renewable facilities using our data. Again, this is AI on top of our data, finding, in this case, wind energy facilities and solar energy facilities around the world to be able to map them. And turns out several of the countries had completely different estimates of how much solar and wind energy that they had. And so it's good to calibrate. And then this is the carbon mapper one that I mentioned earlier. These are all the methane leaks that has been detecting around the planet from various facilities, how big they are. You can zoom into the exact building or facility that is producing these methane gas emissions. And that's all done as a digital public good for the world. Also just wanted to mention, since it's a scientific key audience, that we provide our data in collaboration with NASA to thousands of researchers across the United States and others around the world who do their own research on top of our data in these different areas, now producing, I think, 3 peer-reviewed papers per day, and total over 3,000 now. You can see the steep rise in that. Our hope is that this can underpin not just science, but also applications that help us to take care of the planet. So now I want to switch gears a little bit and talk about how AI is related to space. So a lot of people, obviously, pretty much every sector is being intersected by AI, and space is no different. But I think space is uniquely positioned to leverage the benefits of AI to do some really cool things. We started with CNNs, but convolutional neural networks, but we're really moving into large language models or visual language models and foundation models that can lead to what I call queryable Earth. But yeah, obviously this is quite the revolution. But AI is really about 3 things. It's about the compute, the algorithms, and the data. And a lot of the big foundation model development by OpenAI and Anthropic and Google and others, they're really focused now, if you hear their recent talks, on real-world challenges. They want to build these real-world models to tackle real-world challenges. And of course, if you want to tackle real-world challenges, you want real-world data. So we feel at the center of this revolution that's going on. We have this powerful data set that can potentially help solve real-world challenges. Our data is hard to play with because we've got 45 terabytes a day. So most people are like, what the heck to do with that? But AI can make it much more accessible, right? And just like ChatGPT helps you access all of the information of the text of the internet primarily, the question is, can you imagine what could be done if you could have a queryable interface, a semantic interface to the Earth? And so that's sort of where we're heading next. And the basis of that is the fact that we have these 3,000 images for every point on the Earth's landmass, so we can train algorithms on what's normal, what's not normal, and to detect changes. In many ways, what AI is doing today is, if you're typing in a sentence, it will guess what's the next word in the sentence. It's guessing the next token. And a sort of equivalent statement in our data stack is guessing what the next image is going to be. And therefore, where's the next refugee challenge going to be? Where's the next deforestation going to event? So predictive analytics, I think, is going to take off tremendously over the next coming years because of this data archive. So, and the other reason we feel in the center of this revolution is because we're in the center of this revolution, physically and geographically. A little area of a little part of San Francisco seems to be where it's all taking off. I know everyone thinks that Google is in the South Bay, which it is, but their Gemini team is all up in San Francisco. Everyone's knocking San Francisco, but this seems to be an interesting development. So I'm going to show a few examples of AI using our data. Can you see the ships? There they are, and it caught a plane as well. So this was using CNNs, so convolutional neural networks, and we'd shown it thousands of examples of planes or ships in order to get this working, and that's certainly been helpful. And a lot of people use that, and we did that with planes, ships, roads, buildings, various things, and we can search the world for things like that at large scale now. But that's a particular thing that's taken a particular training model. Now the question is, can we go to more generic ways of searching this database? This is just one more example where we did roads and buildings for the whole Earth, which is cool. And there's a lot of roads that are there that aren't on Google Maps, it turns out. But the question is that I posed to our team about 7 or 8 years ago was, what if we could look at every single object, detect every single object that is on the Earth every single day, and turn that into a database that you could search for all objects over time? Then you'd have some sort of version of queryable Earth. So I gave a TED talk about that, and you can imagine asking semantic questions like these, both of the current Earth or predictive even. And so that's what we started building. And this is a collaboration we did with a partner where it was the first use of large language models on our data, which was really cool. If people remember, there was a balloon that was flying over the United States that, and some people at NORAD called us up and said, hey, can you find that balloon? And we're like, NORAD called you. Yeah, I think they knew where it was, but they were also interested in knowing where we thought it was. But anyway, so we not only found that balloon, but managed to trace it back through time, because again, we have the layers going back. We never delete a layer. And we traced it all the way back to Hainan province where it was launched and found it within an hour and a half of its launch. So digital forensics of the whole Earth start to become possible, because this thing, by the way, had never been trained on balloons. That's the distinction of this new development. This thing, in fact, was sketched a balloon on a piece of paper and shown that. And then it just found it across our imagery. So things are changing to this single shot or no shot learning. And I want to just show this very quick example I did literally the other day. But if you show images, just satellite images to these large language models like Claude or OpenAI's ChatGPT or Google's Gemini, it can actually just start doing analysis out of the gate. So you can go 0 to some sort of analysis of satellite imagery in literally seconds and at scale. So I think the 3 things this is doing is enabling the speeding up of analysis of satellite data, the scaling up of it. So suddenly you are able to ask questions like that previous one was across the whole significant part of the world, but it's certainly the US, Canada, and China. And the third thing is democratizing access. Because anyone can do. Anyone can look at an image, put it into one of these LLMs and say, tell me what's going on. Give me a graph of land use over time, or in this case, estimate tree canopy cover over time. And it will have a go. And it might not be super accurate, but it's going to have a go, and it's a good way to get from 0 to something. And most organizations we work with have teams of people with PhDs in satellite imagery processing, but most organizations in the world don't have those skills. And so we think we can open this up decidedly. So my prediction is that we're going to move towards an ability to search the Earth, just like you can search the internet now with ChatGPT, and imagine the power of being able to do that. And so I wanted to close out with just a couple of slightly more philosophical things, because, well, this is a philosophy and science club, so here we are. I think we're on the verge of some really important Copernican moments as a species. The first is racing towards us, somewhat involuntarily it feels, AGI, right? We're giving birth to superintelligence right here on this planet in the next 10 years. The other couple, though, perhaps are less known, that I think it's really likely that will happen. The first is that we're going to have first contact with animals. And what I mean by that is deciphering animal language with AI and being able to understand what they're saying to each other. And just imagine whales have been speaking to each other for 70 million years. They might have some interesting stories. And it might expand our empathy circles to care about animals a bit more if we understand their social patterns. And then there's the first detection of life off Earth, which I also predict will happen within 10 years. A lot of people can see that coming because of detection of interesting atmospheric spectra that we're now being able to do of planets all around our star system, our galaxy. The nearby is, we've got thousands of planets to look at. We've now got telescopes coming online that can do spectra of these. And one of them is going to find an interesting spectra that we're going to go, the most likely explanation is probably life. And we had a version earlier that year where we thought maybe there was a case, right? It doesn't look like it probably is, but I think that will happen with more definitive nature. To think that we're on the verge of these three moments, all three decentering humans from our anthropocentric ways, I think is really compelling and exciting. And the way I think of planet fitting into that context is holding up a mirror to help us to take care of the planet, and in that by that means helping life helping itself to understand itself. Or even, I often think that humans are definitely conscious at an individual level, but if you think about how we're taking care of the planet, not very conscious at a collective level. Collective consciousness is something that I think we need both great intelligence for, but you also need great sensor data. So that combination, babies wake up and become conscious in part by having sensors and actuators and interacting with the real world, as well as the brain material. So now we have AI coming along together with this massive amount of data about the Earth, and perhaps this can help humanity to become a little bit more collectively conscious, or at least a bit smarter. So with that speculation, I'll leave it, and thanks very, very much for everyone's time.
Oh dear. Okay, well, we have time for questions. So let's start with the blue microphone. Yes.
Okay, hi.
That's a blue microphone.
So wonderful talk. I'm actually really excited, and I'm really excited to play with some of your data sets because I'm pretty interested in machine learning, especially for geospatial. One of my biggest questions with regards to doing AI machine learning on geospatial imagery is I know that some of the data can...
Did you tell us your name?
Oh, Elliot.
Are you a member?
I actually applied yesterday.
Excellent. Now ask your question.
Okay, so simple question. I know that some of the data requirements for geospatial can be immense. You've already spoken that every day you're downloading 44 terabytes of data, and I know even with some of these images, they can be gigabytes in size. So would this lead for you to have a much stronger compute requirement? I think it would even be difficult to fit like an entire satellite image into like one GPU. So are your models just that much better? Are your compute requirements that much better?
Well, actually, this is changing very fast. So one of the most exciting developments I didn't touch on was the work of embeddings. So there's these incredible developments in embeddings, which basically project the images into these vector spaces, but somehow enable extraordinary efficient searches. And that is how the basis of that balloon example. Google DeepMind just came out with a paper on this, which is really exciting, and Meta did too. And basically, that is going to enable the compression, maybe 100 to 1 or something of these data sets to make them basically queryable. The other day, our teams did an incredible job looking at an entire base map of the whole Earth and searching it in under 10 seconds. So you can give it either a word input or an image input, and it will search the entire Earth in under 10 seconds. Just imagine the power of that, right? It's really cool.
I'm going to do more than imagine.
Great, even better.
Red microphone somewhere. Please stand up, tell us your name, and if you're a member, I think I know you.
Good evening, Kirby Runyon. I am a member. Fascinating talk. Thank you. I'm talking from the perspective of planetary science. And my question is, if you keep in mind the most capable spacecraft in your fleet or type of spacecraft in terms of image resolution, what would be some of the largest technical challenges for adapting it for solar system exploration?
That's a great question. I can't wait to try. I think there's a question of the radiation going through the Van Allen belts and what they will, how well the electronics will survive. But I mean, traditionally, our approach to that has just been redundancy. So throw up a few more, and probably most of them survive. It turns out, a lot of these electronics survives better in these radiation environments than you think. So my gut would be not very much. Obviously, you need different propulsion systems depending on your maneuvers and stuff. But I'd be willing to put a wager that if you put 10 doves or pelicans around Mars or something, they'd probably just work.
Ciprian Ivanov, member. How do you manage to get satellites to go that low? Is it low cost results in disposability, or is there some durability factor?
Yeah, so most of our satellites fly at about 400 kilometers. That's not that low. It's low, but you can fly lower. I mean, we're looking to operate pelicans. We name them pelicans because they're low flying, and pelicans get lift off the water when they fly really low. And so we were sort of thinking maybe we should get lift off the atmosphere. Anyway, that's a loose analogy, but it only really becomes a problem when you get down to sort of 300 kilometers. That really becomes hard. But we have ion engines that are keeping them at that altitude so that we can keep operating them. But also we have a design life that's much shorter. One of the things my colleague was always pointing out also with the phone is that just like you don't want a 3-year-old or a 5-year-old or a 10-year-old, certainly, phone in your pocket, you don't want a 10-year-old satellite in space. Because the electronics, the sensors, everything gets obsolete. We call it strapping space to Moore's law. So we've had on average, we've had 39 launches, so on average 4 per year. And every launch we're putting up the next generation sensor, the next generation processor. So in those Pelicans that were launched last week, we have NVIDIA Jetson Orin processors. Is the fastest GPU in space, so that we have more processors in space. We don't even know what we're going to use that for exactly yet, but we be more capabilities driven. And I'm sure there's going to be algorithms that we want to put at the edge to do onboard compute to get certain data and answers back faster. So by doing that, we produce far more data every time than trying to keep the satellites in orbit for longer. And they just naturally decay and hit the top of the atmosphere and burn up. The end of life.
Red microphone. Mike.
Yes, Mike Hilton, I am a member. My question is, do you do anything to your SmallSats to reduce the radiation that it reflects back on the Earth, and thereby prevent astronomers and other people looking beyond the Earth orbit to do their job?
It's a great question. Not a huge amount yet, and a lot of that's because we haven't heard any complaints from the astronomers about our data, basically. Our satellites are very small, and so they don't tend to cause the same challenges that the Starlink satellites have been causing a lot of problems for astronomers. Starlink is about 10 meters long. Ours are about this big, so much smaller, but more mighty.
Blue microphone.
Timothy Thomas, I am a member. I want to ask about the use of your data in actual tactical warfare today. Are people in Ukraine, the Congo, and other active battlefields using this information to regulate their assaults?
Yes, in important ways they are. So our data is being used to, not so much in the kind of way you were suggesting, but more in domain awareness. So battle damage assessment, figuring out where people are doing what. And the most important thing about it is that also we are ensuring that multiple actors can access that data as well. Yes, I mean, well, certainly news media, NGOs. So in Ukraine, there are many NGOs that are using our data, and the New York Times and the Financial Times and the BBC use our data. You would have seen it all over the press in the case of the recent strikes in Iran or wherever, bringing accountability to what's going on. And so we think that that's an important principle because we think accountability drives towards more peace. So, I mean, historically, warfare has been typically driven when countries make mistakes. And that's normally when they don't know about things. Classically, the Cuban Missile Crisis was when the US didn't know the Russians put missiles in Cuba and then discovered them, or vice versa. When the US put missiles in Turkey, that's when things almost got hot, right? When everyone knows what each other are doing, that tends to de-escalate things, and it tends to. So we believe in that theory of change for security, and we lean into it.
Red microphone. Frederica.
Yes, my name is Frederica Derima, and I'm a member. Thank you for the work you're doing. It's, in a sense, a tremendous infrastructure you're creating. How do we, in a sense, integrate that with the infrastructure that NASA has, the Earth observing system?
Yeah.
And let's say take one application, wildfires, where you, in a sense, show that you can map very frequently the vegetation, which is one of the components. But then there is the fire propagation. There are many other observations. There is smoke and propagation of the smoke. So how do you, in a sense, integrate that? And how do you see how your infrastructure scaling? Because it's cheap and can scale in terms of making this kind of integration with the NASA infrastructure. For example, are you working with CAL FIRE in California? And before that, I want to say congratulations for uttering the words climate change, biodiversity loss, and pollution fearlessly.
Frederica.
Of course. Yeah, I mean, so we work, the basic answer is a lot. We work a lot with NASA, the ESA, and our friends there, integrating their data sets. As I mentioned, our Dove satellites and all of our satellites are calibrated to Landsat, MODIS, Sentinel data sets. That's how we calibrate the spectral bands. And then there's, most importantly, interoperability in the sense that thousands and thousands of researchers, probably hundreds of thousands, are using both data sets, right? And then looking at interoperability using both data sets all the time in practical applications and science. So, and we'll continue to do that. We'll continue to work with NASA, see if we can do missions with them, for them, and we'll continue to try to calibrate our satellites so that they are synergistic.
Let's go to the blue microphone, wherever it happens to be.
Right.
And
Phil, not a member, but I brought my checkbook. So I had a question. Do you still take checks? No.
oh yes, as long as they are going to, clear the bank,
I'll leave town quickly.
he'll track you.
So those people don't know, there is an API for this. It's an application programming interface. You can sign up for it. You can download images if you want to. What my question is for Will is, let's say hypothetically, do you look at what your users are pulling down? Let's say, for example, a bunch of IP addresses in country X, all of a sudden 50, 80, 100 of them start pulling images from Kazakhstan or Peru or wherever. Would you say, I'm going to start training data over here? Whatever's happening over here is the next thing based off my users and what my users are doing.
I think it's a very interesting theory of how we can have network effects, because, of course, if there's lots of people looking over here, then we can train more data over there, right? And I hope that we will do that in the future. In general, we're moving less user-driven, more AI-driven. So I mentioned how we have this we have a peripheral vision with the doves. We then have AI that's enabling us to figure out change, and then we have a high-resolution system that can zoom in. It's very much how the eye works. You have a sort of medium resolution in most of your field of view, a high resolution in the center as predators. We have those little high-resolution piece, but we have a very good visual cortex that makes it look like all of this is high-res, and then we're very good at change detection. And if something changes, we can take a high-resolution snapshot. And in that way, it looks like we've got a high-resolution image all the time in our field of view. And we're trying to do that basically for the Earth in combination with that. But I think there is also user-specified things that you get into as well. I think that's interesting.
It was more like, will you use humans to?
I get it. Yeah, I think it's a good idea. We don't do that at the present, but I think, as I said, it's more algorithmically driven. But I think we could do.
Red microphone, AJ.
Yeah. Hi, AJ Katari. I'm a member of the PSW. The satellite that was launched recently, NISAR,
Oh yeah.
the NASA ISRO small aperture radar, is that doing the same thing? Is that like a competitor to what you are doing, or are you going to sort of work together? Because that's also 30 centimeter and 1 meter kind of a resolution or something like that. I mean, two different apertures.
Yeah. Is that a SAR mission or is that an optical mission?
I'm sorry?
Is that a SAR mission, did you say? Is it synthetic aperture radar?
Yeah, NISAR.
Yeah.
The NASA ISRO synthetic aperture radar. That was.
So that's quite a different modality that is then obviously we're relying on reflected light that has to transmit its own beam and then get the received beam in order to make measurements. I think those are very complementary assets, right? You want both optical and SAR often to determine features. Optical doesn't work during clouds or at night. SAR can. On the other hand, SAR tends to be much more expensive because of the energetics, and you have to have a lot more power on board. The duty cycles are less, and so on. So they're complementary in the capabilities that they offer.
Very good. Thank you.
We're going to take some questions from our online audience.
We have a question from Thomas Carr, who is a member from Maryland East Shore. How well can AI detect drones and other UAVs in addition to airplanes?
Well, it depends on the resolution of the imagery you put in and also how good the algorithms are. Right now, our 3-meter scan doesn't pick up drones very much because drones tend to be smaller than that. The 50-centimeter data can pick them up in some cases. The AI systems are quite good. If you can visually see it, probably the AI can see it as accurately, if not more, because sometimes they're using the spectral bands that you can't see and other things to figure out features. But it really just depends on the resolution. We've certainly seen a bunch of drones, but generally that's not what we find all the time.
Second question from Dave Meyer, who is a member. Will Planet have the ability to contribute global carbon mapping in the event NASA ends the OCO missions?
Well, our mission is a little bit different from OCO. The hyperspectral mission, Tanager, can help with some of that aspect, but it hasn't got the wide swath that OCO has. I really hope we continue to have that. Once again, this is complementary data sets. You want the scan and the calibration that OCO is doing, and you want the zoom in that the Tanager does that enables you to pinpoint a source of carbon or methane emissions. So you want both ideally. So ideally, we would continue both.
Thank you.
I think we're up to the blue microphone somewhere.
Hello, my name is Yasmin Moore. I'm not a member and I don't have a checkbook. Sorry. So regarding the case of Ukraine, for example, how do you balance the public availability of the information with potential privacy risks? Like the same way that you were able to see the bridge being constructed, could Russia not observe Ukrainian troop movements? Mm-hmm. And how do you prevent kind of biasing the access side so as not to essentially make the company an enemy of a state while, not necessarily aiding hostile actors?
Yeah, that's a very complicated question. One that we spend a lot of time thinking about, and the first thing I'll just say is how much we care about getting that right, and we spend an awful lot of time considering that as a leadership team, as our board. We have an ethics committee as well that reviews these cases to make sure that we do the right thing in those circumstances. Also, in general, in times of war, we restrict some of the temporal features of our data for everyone so that it leads to less likelihood of challenges happening, and only if they're certified users. So we go from, if you like, a default access to a default non-access over certain regions at certain times. There's still actors like including in media and NGOs and others that can have access, but they've got to just shown us that they've got methodologies to check that they don't put people in harm's way first. So things like that, but it's many hours of discussion, so we can talk more in the bar maybe.
Did you talk to SpaceX at all about this problem?
Which one?
SpaceX about, well, they have a problem with Starlink being a strategic asset and utterly important to the way the Ukrainians are able to conduct and communicate. So have you talked to people there? Just curious as whether.
Yeah, of course. I mean, we talk to people there all the time, but they take a different posture on this. You obviously have to ask them, speak for themselves on that. But I just say that, I come back to the point that we care to get it right and support the people that need it.
We'll go to the red microphone.
Matt Kaywood, member. How do you approach stereo, sort of multi-view, for photogrammetric applications and things like that? Is that something you can do with machine learning, with multi-day passes? Or, as you add satellites, is that something you'll be able to do live? Like, what's the plan for that sort of imagery?
It's a great question. If you want to come join the team, you can come implement it. Actually, I've always been excited by that. And you can, in our imagery, set up tasking with stereo pairs or more to get triangulation. We've got some pretty good algorithms that turn that into three-dimensional maps. And we have partners that do a lot of that kind of work with our imagery. We don't have a central product that just does that natively all the time. But I like the idea of doing more regular, up-to-date 3D models of the Earth. Google was doing some work with our data on flood forecasting in Bangladesh and India, leveraging stereo pairs to see how after the monsoon the whole flooding plains change dramatically, and you need sort of up-to-date data, otherwise you don't know which village is going to be in jeopardy or whatever this year. And so there's definitely projects that use that, but we don't have a systematic program, if you like. But I'd like it. So if you want to come join and do that, that's great.
Get a microphone over here. Hello, Ravi. We're at the blue microphone.
My name is Tijan Beydur. I'm not a member yet. My question is related to the moon. I know you worked with the moon before, and it's becoming more and more important.
Yeah.
It's becoming prime real estate, especially the part that receives sunshine all the time.
Mm-hmm.
So are you looking at that region, or will you be looking at that region in the future, monitoring what countries like China, Russia are doing?
Well, we do call the company Planet, which didn't restrict us in this particular regard. It's not called the Earth. No, but in all seriousness, we're really focused on the Earth with our operation. But I think you're getting at a real point. The commercialization of the moon is really happening, right? We're having commercial missions to the moon now. A couple have been successful. It's really exciting to see that. And I think it's going to be an exciting journey as humans go back there. I think there's an incredible potential to do exploration there. I think we've got to spend most of our energies focused on helping this planet. But, the moon is just, a couple of days' drive, so to speak. And it's crazy not to do some exploration there, some science there. You can do really interesting radio astronomy on the far side. And I think even ultimately backing up humanity is a good thing. There's a seed bank there. I don't think you need millions of people to do that sort of thing, and it can be done relatively cheaply. But again, I think the focus it should be on the Earth. I do think that we have to think about some rules of the road for there. You need a sort of meta-constitution for the moon, like on resource rights and trying to prevent monopolies. You don't want someone landing there and saying, I claim ownership to the South Pole. That would be really annoying for everyone else. So how do we prevent monopolistic behavior? How do we encourage the plurality of interests that we want to happen on the moon happen? That's a sort of unwritten territory right now. So it would be really great to start working on international agreements for how to deal with that.
Jared, could you get the blue microphone over here too? And we'll go to the red microphone first, and then we'll go to the blue microphone.
Yeah, Zamankova, member. Fantastic talk. I think that Al Gore, with his digital Earth, would be in high heaven listening to your talk. Okay, because it was like, digital Earth was a big thing, and it was killed and all that. We all know that. I was really fascinated to see your pinpointing the methane pollution. How about the tiny methane pollution due to fracking? Okay, it's one pollution. Another pollution is the plastic in the oceans, which you should be able to see and detect and point a finger and say, go and clean it up. And finally, your contribution to the pollution when your fleets of things are falling down.
Yeah.
How are you addressing that?
Great questions. So the methane in fracking, that's the kind of thing we can detect with that, as long as it's concentrated above a certain amount, like 66 kilograms per hour, roughly, of methane produced in a source. So it depends how widespread it is and so on. And that's got to be within a 30 by 30 meter box. Yeah, and I look, we're. What was the second one? I actually forgot. Yeah, plastic. Yeah, actually, there's a lot of scientists doing that kind of stuff. Obviously, we don't have the power to tell them what to do, though, thereafter. So I wish we did. But that's the point. The shaming, I mean, it's carrot and a stick, right? It's a carrot because you now have the data to act on, and it's a stick because you can get embarrassed. I mean, I think some of the action we're seeing on oil and gas facilities is just the sort of embarrassment factor, right? By the way, it's an inefficiency for them. They don't want a gas leak. That's just a wasted. So we're really aligned here. We just need to tell them where it is. So we often find they just turn these gas leaks off. They just didn't know existed. So of course, that's win-win-win. Win for them, win for the planet, etc. So great. Yeah. And the final one again? Oh, I was trying to forget that one. No. Well, sadly, I mean, we did an assessment. We do an ESG report every year, and we did an assessment that most of our dominant impact is nothing to do with the satellites. It's stupid executives like me traveling around the planet on planes. So that's what we've got to reduce, to be honest. Rockets contribute a fairly minimal amount, and then the re-entry of the satellites into the Earth's atmosphere is also extremely small. We're talking about a tiny, tiny amount of mass every year. Even if you extrapolate that's the kind of constellations that may be existing in the future, it's going to be really, really minimal. I think our problems are mainly the ones that we all face down here.
Marcia.
Marcia, sorry. So I was going to ask about the space debris, but I'm assuming your satellites burn up so that they don't become space debris, right?
Correct.
Okay, and then I just wanted to make a suggestion to this comment about the moon. The Antarctic Treaty was actually signed here in Washington, D.C. at the National Academy, and that might be a good model for coming up with a moon treaty and doing it sooner rather than later, because it was so important that that Antarctic Treaty was signed at the beginning of the last century.
I 100% agree. And by the way, the debris challenge is a real one, though, orbital space debris. We keep our satellites really low so they re-enter, as you pointed out. But we are seeing a huge number of satellites going into higher orbits as well. And that can be really challenging. Even if you have propulsion on there, the challenge is if 1 in 100 of those satellites, the propulsion system fails, you get a real challenge. And so we have a challenge of space debris, and we are in a Kessler syndrome now where we're running away from 800 to 1,200 kilometers. We have a runaway situation. So it's getting worse. Even if we launch nothing into those orbits, the density of objects is going up because of collisional cascade. But there are ways of dealing with that, like grabbing really large pieces that become the source of future growth, or using, one scheme we came up with when we were at Ames was using lasers to nudge the debris to try to stop collisional cascades. So it turns out you only need to nudge them a tiny bit so that they just miss, and then stuff naturally eventually comes down. So with a tiny amount of photon pressure, you can sort of do traffic management of debris. But anyway, we need to fix that. We're on an early part of an exponential, so it takes a while for this to be a problem. Hopefully, we won't put our heads in the sand about that one as well.
My name is Mary Paulet. I'm a Perspective member. I'm also the CEO and founder of QuarkTime, which is an AI in the public interest company. I had a thought. I'm not sure if any researcher has explored this or not. Do you know, is there any research that has been done as far as trying to harvest rare earth minerals from a comet?
Probably better people in this audience to answer that one than me, to be honest, or the previous speaker. But Not that I'm aware. I mean, there's lots of people have talked about that for
What
years.
was that guy's name? Ledecky and
Lewicki? Chris Lewicki?
Yeah, who had the
Planetary Ventures, yeah. Yeah, there's been companies that have tried to do this. I don't think that's a business plan right now. It's very, very difficult. So it's a long way off, I would say, technologically, for it to be anything useful.
I'm going to sneak in a question. It's bothering me. The methane leak map, there were two really large leaks, and they were both in the south of the U.S. They look like they were Texas and Louisiana.
Yeah.
Have they been remediated, or what is the reason? Because you'd think maybe the Middle East would have, big methane leaks also. I didn't see anything comparable.
There are some over there too, but yes, Texas has a lot. Yeah. The one that was fixed was in Texas as well. So yeah, we're trying to expose it best we can. I don't know why they're bigger there. That's interesting. Everything's bigger in Texas, isn't it?
That is a loaded question I'm not going to answer.
All right.
All right. Done? So what are we up to? Maybe one or two more questions. We've got a red microphone here.
How did you get so many? Oh, David Rosen, lifetime member. And how did you get so many satellites in polar orbit?
Mm-hmm.
That's basic.
We put them in on polar launch vehicles. Last week was a Falcon 9 from Vandenberg Air Force Base. But I mean, there's relatively regular rides into polar orbit. It's the most popular orbit because it has this nice feature of you can cover the whole Earth and you can stay fixed with respect to the sun. That's the sun synchronous, so it's really a super convenient orbit. So actually, it's probably the most regular place that is launched to. Okay. Yeah, we've had, I think, as I said, 39 launches. Most of those, I think, apart from all about.
It isn't one satellite per launch, is it?
No, we typically launch a few dozen. On average, I think we've launched 20-ish per launch for these 39 rockets.
We'll go to the blue microphone. Aki.
Yeah. Aki Roberge, member. Thank you for a wonderful talk. I appreciate your focus on actionable data. Yeah. I wonder, do you take any actions to make the actionable actions? Do you do anything to help that, or is it more of I build it and they come?
Well, we do. Yeah, we do. We help to form consortiums of people that are working like this. Alan Coral Atlas was a consortium of NGOs and universities and nonprofits that are trying to do conservation on coral reef systems. We'll obviously try and do our best. We can't do all things for all people, but we try to help the accessibility, right? I mean, the best thing we can do is make it easier to use, which is why we're focused on this AI piece of it, helping it make it easier for everyone to get access to that. So that's why.
So one of your slides answered that question as well, with the 55% reduction in deforestation.
Yeah, that's a big deal.
Yeah, that's a big deal. Yeah. All right. Well, I think that. Oh, red microphone. Sorry, and it's a new person. So.
Hey, my name's Oscar Weigel, not yet a member. Thanks, Will, for being here. Really appreciate your time, and the talk was fascinating. I've got a lot of questions, but maybe now wouldn't be the best time since we're wrapping up. It's just a fun question. So since commercial space travel is becoming more viable, and say planets, stock takes off and you become one of those billionaires that can shoot themselves into space, given the opportunity, would you yourself want to go into space, or have you seen enough pictures of clouds?
No. I would love to. It's not a big focus of mine for my life, but I would love to, most of all, to go to the moon and get the perspective of the whole Earth, not just go into low Earth orbit. I know that's even more expensive, probably, but it would be amazing to see what the Apollo astronauts saw. That really gave them more than just that overview effect, that sense of us being on this fragile little planet with a thin atmosphere around it, protecting us from the rest of space. And I think I love the idea of more people getting that sense, so that, because from that perspective, it's obviously we should cooperate and all those other good things.
We're going to wrap up with this one last question. We got one last question. Blue microphone.
Robert Thompson, I am a member. So at the very end, you mentioned something kind of interesting, which you said that a consciousness emerges in a child because of sensory input, or maybe it's coupled to sensory input. And I'm not going to debate whether that's true or not, but I've also heard from some other people that study AI and AGI that they suspect that AGI requires some sensory input in order to achieve some AGI, or maybe we go beyond AGI to some kind of consciousness in silico. Are you of that kind of view? How do you see planet's role in being the sensory input to an emergent AGI?
Well, I hope we can, because I hope that will, maybe this is naive, help that AGI to care about the physical world and the life on the planet more, if we can tell it more about that. But yeah, I mean, again, this is sort of also a naive picture, but I think that interaction with the sensory world is critical for babies' development and becoming more aware, self-aware. And so, I don't want that AI just focused on the internet, on the text of the internet. I want it focused on helping the whole world, and maybe that will help us to get a bit smarter collectively as well as it does that. Look, I admit that that's just sort of vague, but right now it seems clear that we're stepping on the gas and deciding to do AGI. We are making that collective decision as a species, which is really exciting and also terrifying at the same time. And but the best thing I think we can do, given the fact that it seems like we're doing this, is I think try to make it care about life and try and align it to the interests of life. And I think it will, at some level, naturally do that, because if you wake up and figure out human knowledge, a lot of that could be summarized by we're a little set of species on one little planet in a big universe that's mostly dead. And I think AI will quickly realize that, and therefore may take care of the life on it. But it's a bit of a hope but helping it with this kind of data is one step towards perhaps improving its if you like, quotient of alignment.
So, thank you.
No worry.
Before you go, we have a few tokens of thank you.
Thank you.
Which include a framed copy of the announcement of your talk, a PSW rosette, and a copy of Volume 17, first edition of the PSW Science Bulletin, founded as the Bulletin of the Philosophical Society of Washington, since you wanted to talk some philosophy. You'll find in there the original founders and why they founded it, why they called it the Philosophical Society. And you'll find also some paired minutes of meetings, including the first this presentation of the cause of yellow fever, and then, of malaria. And then later, more recently, a talk on genetically engineering mosquitoes so they can't propagate the parasite.
Yep.
And there are things like that. So
cool.
It's a kind
Thank
of
you.
interesting read on a plane when you don't have enough mental energy to do anything more demanding. And with that, we thank you very much for...
Thanks a lot. Thanks a lot, Larry.
Thank you.
Thanks.
So before we adjourn to the social hour, there are just a few things to announce. Mostly our next talk is going to be Peter Shaw. So who is Peter Shaw, you might want to know. Well, at the 2521st meeting, the inventor of Shor's algorithm, which showed for the first time that quantum computers can outperform conventional computers on certain computational tasks by orders of magnitude, threatening the very foundations of security on the internet, among other things. He will discuss Shor's algorithm and explain how quantum computers work, why they're better for certain computations, and the prospects for computation in the future, quantum computation. After that, we have at the 2522nd meeting on October 3rd, Adam Rees, professor of physics at Hopkins, and co-recipient of the 2011 Nobel Prize in Physics for discovering the acceleration of the expansion of the universe. Some of you may know that we have something called the Hubble tension. It's a difference in the measurements, very careful measurements of the acceleration, the rate of acceleration of the expansion of the universe by a couple of different methods, 3 different methods, and they don't agree. And all of the efforts to interrogate these measurements and find faults that would allow these different values to converge have failed. And the more they look, the more the values by each different method end up being whatever that value was. And then the uncertainty bars get smaller and smaller, and the differences don't change. So the question is, what does this mean? Does it mean that there's physics out there we don't understand? Does it mean that there's a systematic mistake in the assumptions that underline these calculations by which we derive the Hubble constant from the measurements? And Adam is going to come and talk to us about that. There are 2 talks, previous PSW talks, that you might be interested in if the subject interests you. Adam himself talked at the 2522nd meeting on October 3rd. Whoops, I said the wrong thing there. At the 2261st meeting on December 4th, 2009, before he won the Nobel. There are written minutes on the website, but there's no video because that was before we did video. And Wendy Friedman, who is the principal investigator of an alternative method to the one Adam Rees uses. Hers is based on Cepheids, and his is based on supernova type 1a standard candles. She gave a talk, and there is a video of that talk, and she talked about the Hubble tension at the 2428th meeting on November 6th, 2020. Other upcoming lectures are listed in this slide, and I'm not going to talk about them very much. You can go to the website and you can see a list of the talks that are upcoming. About 10 days in advance of all events, PSW sends all members invitations to the pre-lecture reception and dinner with the speaker, and notices of the lecture itself are sent to everyone on the PSW Friends list. Feel free to join PSW, and if you don't want to join, you can still sign up for notices of the lecture on the website. And with that, let's just thank the people who did the cameras and ran the video on the back. Thank you very much, and with that, I'll entertain a motion to adjourn the meeting. Second? All in favor? All opposed? Meeting is adjourned to the social hour. There are refreshments in the back of the room.